My name is Justo. I'm the founder of Shapelets. We are a startup company. To be honest, it's actually quite good to be outside because we've been really working in the dungeon for a couple of years now creating this platform. So it's really nice to come to the PyCon today and actually do the first open presentation of something that we've been working on for a while now. I believe it's quite interesting, and it's all to do with an area of indexing databases, indexing data on the move, indexing with AI, and so forth, which makes it quite interesting. So the talk today is going to be shaped into different areas. There is going to be a little bit of a set of a context explaining what is Shapelets and what is it, what you're going to see, where it fits in the overall picture. And then we will see code if nothing happens. You know, live demos are always tricky. If nothing happens, then we will see a couple of examples of using Shapelets REC in the context of an embedded library, because this is quite important. Shapelets REC can work as a server, but you can also put it inside your systems and basically accelerate whatever happens to be the problems in your domain. We are a platform company. We are not selling a single-shot solution for a specific problem. So what we like to say is that we like to help data scientists to become really fluent on their jobs, and that is a little bit what Shapelets is all about. You can conceptualize Shapelets as split into different areas. One has to do with interactivity and deployment and stakeholder interaction, rapid application development, really cool widgets, and so on. That's something that my colleagues are actually showing during in the desk that we have at the entrance of the conference. And if you haven't seen it, just please come and say hello to them because they will love to show you around. We are going to focus on the less visual part of the platform, which is what is happening with the storage system. And in here, we have a really versatile system for interacting with any number of data sources that you might have in your organization. We have, obviously, connecting to a number of systems. Could be just data lakes, transactional databases, and so forth, but we also have our own storage. And our storage has the capabilities of actually optimizing especially tabular data sets, especially those that comes in time series. And most importantly, we are going to talk today about this last component over here, which is what we call the vector database and the linear storage system. So if there is any questions, I've been told that there will be run at the end, but if there is something urgent, I really don't mind actually to be interrupted, and then we can attend those questions right away. So this vector database and this linear storage system, where does it fit within an overall picture in an organization? The bottom up of this slide is actually trying to show you what people normally do in a company, which is I got my data sources, could be almost anything that you can possibly imagine. And then I got a first point of data acquisition, and in here you got different set of systems, could be historians in Industry 4.0, for example. You can have logs, you can have all sorts of different information in this area over here. Let me see if I can highlight at least. Never mind. Then, right when you have all that data, then you usually set a team in your organization which is responsible for your data lake. And they take usually care of data normalization, data storage. You end up having like 1,000,001 Parquet files in your organization that you don't know where they are or what to do with them. But mostly, they are actually, they make sense from the perspective of the history of some of these companies. We work quite a lot with the petrol industry, and in those companies, it's actually quite quite interesting to see how the effect of the process engineer in those organizations still have on the data formats and the data payloads that end up stored in the data lake. But then, us as a data scientist, we usually are not so much interested in a very well-known format of data, one rules everything type of approach, because that is actually, in most cases, is going to stop you asking asking the right questions to your data. So in here you have problems like I am keen to understand failures in the data. So I'm not interested, for example, in understanding what is a normalized view of the world. I'm actually interested in gaps in my time series. I'm actually interested in all sorts of different areas that team over there is actually hiding from me. And then issue usually is that I cannot go back to the original sources because they are either too expensive or too complex, or I simply don't have permissions to go there. So the vectorized system that we propose and the linear storage system that we will see running in a few minutes sits in this bottom area over here. So what if, instead of actually normalizing the word as it happens, we had the ability to actually store every single thing that passes through our door. This is what we call the linear storage. Super powerful system that we develop. Is able to basically saturate disks whenever we actually place it in production, or saturate network on the other end in excess of 100 million messages per second. That's metrics in this case, not Word documents. And actually what it's doing is actually recording absolutely everything that passes in front of you. It's read once, read many times. So it's almost like a notary of what is it true that you knew at a particular point in time. And this is very important because if what we do on top of this is actually create a vectorized index engine that is able to answer questions, really complex questions, some of them driven by AI, to that storage, then what I end up doing is actually creating a virtualized data lake environment where the data scientist asking the questions to Shapelets REC is able to recreate the exact data frames, the exact data sets he needs to basically attend their business demands, their applications, or whatever else. Moreover, since this is virtual and then we are actually creating those on demand, we can actually pop them up whenever it's necessary, without having to resort to a single centralized data infrastructure that is very costly and sometimes a nightmare to manage. So that's basically what these two technologies are all about. So what we have there is Shapelets REC, which is connected to your event systems. Could be Historians, LQTT, PI, Kafka, whatever happens to be your poison. We have open API. We have an open API that, if we don't have a connector, you can just basically write your own in a GFI. It's actually pretty simple. REC itself can actually run just in memory and local, memory local, and extending to the cloud in such a way that what you end up having is a virtualization of your storage system. It's almost having like a recording tape that goes back to the very first record that you ever saw. REC takes care of actually going up to the cloud, download whatever information is not stored locally, and it does all that, all those operations for you. And then, so REC therefore is very much document oriented. In some cases, I had conversations with people willing to kill some of those very famous document stores out there that everybody uses in favor of this, precisely because of the speed or the flexibility that you will see in a second. So what we have here is a fully row-oriented system, extreme speed, completely schema-free, and this is very important. You can store in REC things like a voice conversation, video, images, as we're going to do in a second. You can store metrics, an event log or a text or whatever it happens to be. Since it's read-only, this is actually pretty important for some industries like the one that I used to be on, which is the financial industry, where you need to keep your records for audit and regulatory purposes for many years to come. Same thing happens with medicine and other areas over there. And then we have the rest of the platform over there, which is inverting the orientation of the data. We move here from a document-oriented view of the world to a columnar, very optimized columnar store of data that basically can be recreated from the contents of REC, helping you out creating your data sets and therefore using the rest of the platform for creating visual applications and the like. From the point that RECs starts serving information, it talks Apache Arrow, so you can basically, you're at home. So you don't have any form of login factor with us or anything like this. You just can connect it to whatever happens to be your libraries of choice and so forth. Yeah, we are pretty fast. This is a test that we ran the other day, and yeah, we are pretty good writing information. And I can, if you guys want to delve a little bit into this test, you know, we have big names there, not necessarily in the space of vector databases, but we are coming quite far away from what people are normally do. If you're interested to know how this thing works internally and how we have write warranties and all that type of stuff, come and talk to me later on. Yeah, so this is it. That's my slides. So we are going to go to demo now. So I have two demos for you, yeah, because I didn't know very much the audience, so I tried to keep the demos a little bit simple. But if you're thinking about a scenario which is perhaps a little bit more advanced, or just grab me later on and we can discuss it. So we are going to be using the vectorized index engine for in both demos, and the linear store we will be using it for the image classification. And yeah, so that's basically. I'm assuming that everybody's, since it's a Python conference, everybody is happy with Python. So let's move on and have a look to the code. Everything good so far? Makes sense? Good. Right. So. Can you guys on the back see the font size, or shall I make it a little bit? Yeah? Okay, good. So I'm going to sit down for this. Huh? We will be uploading. I haven't said this. Shapelets is completely free to use. It's not an open source product, not because we don't believe in it. It's just because we don't have time to manage a community. It's just a few of us, and it's busy enough already. So it's closed source at the moment, but it's completely free, and it will remain completely free for individual use, either at work or either at home. So you are one pip away from having it set it up in your machine. So yeah. So if you guys are interested, just let me know later on. So what we're going to do in this problem is actually really simple stuff. I'm sure you guys have done something along those lines at some point. So I'm not sure you guys might be familiar with a library called S2 from Google. It's what drives Google Maps. You know, all these boxes within boxes in Google Maps and the like. So what we are going to do is basically, it's a very simple. My wife is from Cuenca. So when I was preparing the demo, I got on the map, and actually I point out in the map places that I knew in Cuenca. Torremangana is a really nice place. Las Casas Colgadas, hopefully you guys know what they are. This restaurant is actually pretty good, and so forth. And the problem that we're trying to do here is, right, if I got a series of events, yeah, and those events have latitude and longitude information to it, how can I query those, say, in a circle? I'm not going to do anything more fancy than that, just basically in a circle, and I want to just basically access that data or identify the data that belongs to that. So for that purpose, we use our vector engine. It's actually pretty useful for those things. And what we're going to do is actually run it beforehand. We're going to prepare the scenario with S2. So we just go off and run it. And this is going to prepare the query area that we're going to use to identify which points belong in that area, right? And now we're going to, so this is done, fantastic. Now we're going to add a few points. Let me just make this a little bit there. With the points of interest, and this will be how typically you will do it in S2. So you basically just ask whether this point belongs to that particular area on an individual basis. This is pretty optimized, so it's actually the right way to do it. And that basically tells us, out of those 5 points that you just ran, 2 of them are within that circle. Cool, fantastic. So this is how you go about doing it with shapelets. So you can instantiate an index store. As I said, this runs perfectly fine as a library within your system. This is a highly multi-threaded system, so it's going to spawn threads in the background, all sorts of stuff, because performance is key for us. And we are going to just create one of the indices, which is particularly efficient for geographical information. And we are going to basically add those points to the index, close the index, and publish, in this line, the index to the index store. So you can actually, this is a very important point, because when it comes for proper vectorized AI-driven, model-driven indexing, you just want to fan out the index creation and later on send deltas to the store. It's far more efficient than doing it in the same server. So we respect that deployment model, and that's the reason why you build it this way, and then you upsert the index to the server. And now we just go into query, and then we have a set of functions here. This one is the cover by, which is specific for geographical information, and we're going to basically say, hey, database, give me all those points that are covered by this list of cells that we created before. Execute the query, and basically print out the results. A few things happen here, which is quite important. Firstly, the result that you get is a compressed bitmap. So you can query something that returns like 1 billion documents, and it still will fit in your will still fit in your memory. And secondly, the reason that you prepare in one hand and then execute is because Shapelets REC allows you to have a query in continuous standby mode. So you always can recreate, requery again, and you will catch up with the latest information that has arrived in the storage system. And that is pretty cool, because it allows you to basically either run your alerts, your AI models at their own page, and then let the data batch up in the meantime, knowing that it's being kept for good, right? So now we're going to run it. Okay, hopefully the answer will be 2. Otherwise, yeah, there you are. Okay, so say like, interesting, but what's the point over here? So let's think about this. Now what we're going to do is, instead of dealing with 5 points, which is really, you can do it by hand, then let's create 1 million of these points, yeah? So we have 5 here, so we're going to iterate 200,000 times just to get to those. So just creating the list of the points for S2 to process, and now we're going to run the algorithm again with S2. Okay, so that basically went like 1.44 seconds, which is kind of reasonable. It's pretty optimized. That library is actually pretty good. So now we're going to do the same. Now we're going to update our index, upsert again, sending the delta back to the server with the new information. So as you can see already, the time to process those has diminished a little bit. And now we're going to run Shapelets again with the results. I don't know if you noticed the execution time, but let me put it in a different way with a good summary. So it's 613 times faster than the optimized library from Google that drives Google Maps. So it's quite interesting. Also, in terms of memory size, having that information to query on your main database, in this case it's just 1 million points, it's not that much. It's about 15 megabytes, but that will be the size, the persisted size of the shapelets index that we created is 4 megabytes, which is extremely low in comparison to the original data, right? So this is one of examples that you can use this part of the technology that we are proposing to your own benefit. Really high speed, much better optimization in terms of execution times, therefore more capacity, more back for your money. Any questions so far? Good. Yeah, go ahead. Yeah. Yeah. Right. So there are. No, you don't. No, you don't. So for this particular type of index, we use something which is called compressed bitmaps, right? So we run RRE encoding on those indices that are basically usually happens quite often. For example, when you are measuring a temperature sensor, you don't get big drops and so it's usually quite continuous. So that basically means that encoding at the index level is very similar to the previous one, and that results in massive compressions in terms of the memory utilization. The geo index is not one that gives you much choice in terms of what to do with it, but for example, when you index numerical data, as we are going to do now, then you can choose how many precision digits do you want to keep in the index, which are an exact representation of the original data. And then that index, you can always query that index, so you can lose the data and extract the data. We haven't published them yet, but we have done some algorithms for do summarization, averages, all sorts of statistics directly over the index, which is actually pretty cool when you think about it, right? Cool. So second demo now, and which is a little bit more funky. Right. Shapelets REC comes integrated with connectors to run your AI models elsewhere. One of those is HuggingFace. Hands up, whomever has worked with HuggingFace before? Yeah, okay. Which is a great system, by the way, to publish your AI models and interact with those. So Shapelets REC is completely integrated with them. All the pipelines that you can run in HuggingFace, from image recognition, categorization, and so forth, you can run them directly as part of an indexing workflow within Shapelets REC. So, which is precisely what we are doing over here. We are using our own representation of what is a HuggingFace model. We are going to choose TensorFlow as the network, as the underlying computational system. Then that's the model. That Google VIT is a model for recognizing objects in images. You can basically pick your venom in the sense that you can put whatever model you want over there. And we are going to set some parameters for the indexing in this case. So we are going to say, like, we're going to need a non-minimum score. We are going to select the 5 most interesting things the model is recognizing from an image. And we are going to cap it with 3 decimals, which is what I was referring before. The underlying index is going to be 3 decimals true to the original values. And finally, we're just going to create a pipeline within Shapelets REC that is capable of receiving images and index those images, right? So this is what we are doing in this very first scenario. whenever you run TensorFlow, it's always bad happens, and this case is the network. Okay, disconnect. Let me just. This is the reason I kept my phone close by. Okay, just give me 1 sec. I can't believe it. Hold on. Sorry guys, it will be just 1 second. Okay. Sorry about that. Let's restart. But at least you can see that the demo is for real, that I'm not making things up. Okay, so let's see if this time it goes through. Yeah, good. Right, so that's TensorFlow booting up and floating with nonsense message as it always does. Okay, so are we done? Yeah, okay. So now we have created this task, right, which is going to run that model. And now we are going to instantiate those two components that I was referring before. We're going to instantiate the store and the indexing side of things. And this is what we do over here. So we are, actually, before we do that, I'm just going to delete the existing data. Right. So what we're going to do is create a local archive system. We are not going to the cloud. It's risky enough already, which is what we call the shelf. And all the data that we are acquiring, we're going to store it in a directory called log. We are now going to run a storage pipeline that you can customize, by the way. This is something that is completely open, so you can actually put your own components here. So we're just going to compress the data on disk. We can encrypt. You can run all sorts of different things in this shelf component, and basically just create the two storage systems: one for the index, one for the log. Okay, so off we go. We are up and running. And I got here. I wasn't going to be very ambitious with my luck. So basically, I'm going to go to the internet, grab 3 images, and pass them through the indexing pipeline. So the indexing pipeline goes like, store the document. That goes back, and it will give us a unique document ID that we can use it for the vectorized system to localize the document later on. This is basically that doc ID. And now we are just basically indexing, running the model, that pipeline that we created before, and just basically that gives us the results of the indexation for those 3 documents. So hopefully, when we run it, yeah, there you are. So we are detecting different things, as you can see. So we are basically producing score labels in each one of those images. So we're just getting a palace, monastery, castle, blah, 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 teapots, always teapots in these examples, coffee pots, blah, blah, blah. And we got a tiger, a jaguar, and all sorts of different things. Okay, good. So as I said before, now we have those indexed locally. Now we're going to publish them to the store to make them public, because that way you can always run 1,000 of this logic in your cloud infrastructure to cope with the load that you might have. So we're just going to finalize. That is, as you can see, it's giving us all the indexes that it has detected. And now we're going to upload them to the server, which is almost immediate since it's running locally. Okay. And now we're going to use that very same syntax that we used before to just basically ask the system, hey, I'm interested in anything that has a teapot, which is this sentence over here, and something that has a coffee pot, or is a coffee pot with a 50% chance of being correct. Yeah, and so we just run that query, execute it. That comes back with just one document out of the 3 that we just put there. And now we are going to ask the store to give us back the information as per the results of this index. And here we are. So that's the link. So hopefully, yeah, it's a teapot. Nice. So it has worked. Yeah, so again, this is completely down to you. I'm using images. You can use voice to text transcript. You can use any model. We are completely transparent to exactly what is it what you do in that moment. But we are really good about helping you out, storing that information super fast, super efficient from memory up to the cloud, and to retrieve that information by basically looking for, having really cool indexing technology for all sorts of different things, from embeddings in one end down to very simple Boolean flags, as you can see with this teapot over there. Yeah. So just to make sure that we can actually change that, and actually let's look for a palace. Just a palace. Anything that a palace is mentioned. Okay, so that will be the query. And we can try to run it again. There you are. Run, execute. Only one document again. That's the link. Yep, that looks like a palace to me, right? So that's it. That's what this talk is all about. So if you guys are into this sort of things, I think you will find a really cool technology that you can either embed it in your own systems. You can use it as a server component. It's absolutely fine. We are in Amazon and about to close with Microsoft again, so you are just 2 clicks away of having this system in the cloud. And and it's completely free for your personal use, so you can actually download it, play with it, extend it. There are APIs absolutely for everything, so you can extend it from either C++ or from Python, depending exactly what you want to do. Perhaps one might be a good idea versus the other. And yeah, and that's basically what underpins our storage strategy and indexing strategy. Hope you guys like it. Thank you. Any questions? Thanks. Yep. No.
Trade-off or engineering decision that the user should be aware of regarding the comparison with other vector databases, because you saw that your performance is much higher, and
yeah.
Do you have any important trade-off versus other vectorized databases?
Yeah, we are.
You are just better.
I think they have more trade-offs with us than us with them, to be honest. Let's see. We are new in the space, so it's a leap of faith to trust us. That's for sure. But I don't know. I come from the financial industry. I used to be a quant in investment banks, So we were doing masses of data when nobody even knew what data science was. So when we built the system, we were thinking is like, what is it what I would love to have in my previous job that I incorporated here, yeah? And this is what we're trying to do, which is really provide tools, not solutions. You see what I mean? And this is very important for us, because if you take Shapelets and you put it up there, it's not going to do anything for you. And perhaps some of the other guys, they come with perhaps a more elaborated solution, plug and play type of experience. We are a little bit raw in that end, yeah? So we are very much at home when you use us in your scripting with Python, you customize our behavior. That's where the place that we are happy. If you're looking something that is, I plug it in and it's there, perhaps this is not the system for you at this moment, because to be honest, it is, how many of us coding? How many of us coding? Is 5 of us, yeah. So it's, you know, it's been a challenge to even reach this far, yeah? But we are, if I'm not mistaken, the Docker that we use for the comparisons, this is something that we're going to publish, yeah? So then, which is nice as well, to be fair and open, because obviously if there are better things than us, then yeah, that's good to know, yeah? Any more questions? Anyone? Yeah?
So to store embeddings, you don't use anything like any other technology like face or noise, so it's all built in?
Nope. No, we don't. No, we don't, because it's too slow.
Okay.
It's really embarrassingly slow. And to be honest, the problem, this is something that strikes me as very odd, to be honest, because sometimes our industry goes in like, is very it's almost like hipster oriented. Yeah, this is the trend, everybody goes and follows there. But the problem of vector similarity is something that it was found an exact, precise, and optimal solution ages ago. And that was the reason why we never, in the 90s, beginning of the 2000 year, we never see any database system providing a KNN type of access, because those index were really slow, and nobody wanted to use them. And now they come back, either in graph form, as Microsoft is doing, for example, or in a cluster partition spread type of way, like Facebook and other guys are doing. There is something which is rather cool, which is called the Fourier transform, that really moves your multiplications down to summations. And to understand how close one vector is another, just do the Fourier transform, do the Fourier transform, do the inverse, boom, you're done. You have the exact solution. And that is highly parallelizable. There are libraries out there that are immense in terms of the performance that you get. And the only thing that you're doing is actually doubling the amount of points in your vector because of the Fourier transform. And, but that is a blob that you can, in very simple terms, you can store it a line in memory. So basically you just map it into your memory, run the Fourier transform, and you get your answer back. And it's the exact answer. It's not even close. No, it's the exact answer. And so why do you want to waste your time with really crazy stuff? It's something that I never understood myself. So we are not using any of those, no. We just moving more, a little bit more like math-oriented type of way of resolving these problems.
And this wasn't just everything in memory, but instead of resistance, you use arrow.
In some cases, we use a tweak version of arrow that is that allow us to write. It's not read-only. Yeah, so we tweak it in a way that allows us to basically do rewrite in arrow format, which is kind of cool. But this store in particular, it just stores the blobs of data as they come. It doesn't really bother to do. It doesn't need to, if you see what I mean. So all the indexing is happening because of the AI models or whatever else, and then from that moment onwards, the index is kept in memory, because it's compressed, it actually can fit as much as you want, really. And then the information actually lives, has a second life on its own right, yeah? So you can actually delete all the data you have in the archive, in the shelf, either on the cloud or locally, and the index will still be valid. Any other question? All right, cool. Pardon? Okay. We just been told that we have an open challenge in our desk. If you guys want to participate, it's actually comes with a sizable voucher of money that you can spend in Amazon. So if you guys want to give it a go, just by all means. I mean, just come about to the desk and say hello. Okay. So yeah.
Do you see that the fact that you're not open source can be a problem for adoption?
Yeah, most certainly. I'm a fan of open source, but the problem is that in Europe it's very difficult to get a sizable funding. We are invested. We are very lucky. We have a really cool investor actually, and but to actually drive something efficiently in the community, you really need a lot of manpower. And at the moment, we couldn't do it. We are thinking of becoming open source at some point, because why not, to be honest? I actually think it's a good thing to do. As a matter of fact, we are giving our software for free at the moment. But it's mostly because we don't have enough fingers in our hands at the moment. That is the main reason that we are not doing it. Yeah? But everything will come, step by step. But to get a community to work, is you really need to push it and you really need to work it out. It doesn't happen by magic. It never does. Cool, nice. Well, thank you so much. It's been a pleasure. Thank you.